a tiny building block of everything around you, yet it behaves in ways that just, well, defy common sense.
Yeah, we're talking about the free electron. You know, the electron when it's not bound inside an atom.
Right, the particle responsible for, gosh, electricity, magnetism, those old CRT screens. So much stuff.
It really is one of the most important particles we know. But figuring out its true nature, that wasn't simple at all. Took decades of really clever experiments.
Yeah, each one sort of chipping away at the mystery.
Exactly.
And that's really our mission for this deep dive. We've got this stack of sources here looking at the key experiments that uncovered the fundamental properties of the electron.
Right. The goal is to pull out the crucial insights. You know, how did we figure out its charge, its mass, that really bizarre wave nature?
And its spin. Can't frig its spin.
Definitely not. So we're going to trace this whole scientific detective story. Some really ingenious setups involved.
Like shooting beams in vacuum tubes.
Right.
And suspending tiny oil droplets.
Yeah, and scattering electrons off crystals. Even that famous one where a single electron seems to go through two places at once.
And why should you, our listeners, care about experiments from, over a century ago?
Well, because these discoveries, they're the bedrock, the foundation of quantum mechanics.
Which explains the whole subatomic world. And that, in turn, underpins countless technologies you use every single day. Your phone, computers, medical imaging.
Absolutely. So let's maybe list the properties first, the things these scientists were trying to pin down.
Good idea. Okay, so first, were they actual discrete particles?
Then what was their electric charge? That fundamental unit, yeah. Is it negative? How much?
And their mass, this tiny value me.
Then came the really weird one. Could they also behave like waves? Like light does.
The wave nature, yeah. And finally, spin this idea of some kind of intrinsic angular momentum.
Exactly. Particle charge, mass, wave, spin, those were the big unknowns.
And the first clues really came from those glowing vacuum tubes, didn't they? Way back in the late 1800s.
That's right. The story really kicks off with the cathode ray experiments. Scientists were seeing these mysterious rays coming from the negative electrode, the cathode, in these evacuated glass tubes.
When they cranked up the voltage?
Yeah, high voltage. J.J. Thomson's work, particularly around 1897, was absolutely key here.
So what were the rays actually doing inside these tubes?
Well, they traveled in straight lines, cast sharp shadows that strongly suggested particles.
Okay, makes sense.
But more importantly, they were deflected by magnetic fields. And the direction told them, okay, these things carry a negative charge.
And Thomson also used electric fields.
He did. He confirmed they bent towards the positive plate. So negative charge definitely locked in.
So negatively charged particles, got it. But how did he make that leap to saying they were fundamental bits of all matter?
That was crucial. He noticed that the properties of these rays, how they bent in the fields, it didn't matter what the cathode was made of.
Oh, really? Any material?
Any material, or what little gas was left in the tube. It was universal. That suggested these particles weren't just some quirk of the setup, but something basic inside all atoms. He called them corpuscles first.
Corpuscles. I like it. And his big quantitative result was the charge-to-mass ratio, right?
Precisely, the EAM ratio. By measuring exactly how much the rays bent under known electric and magnetic fields, he could even balance the field so the beam went straight.
Clever.
He calculated that ratio. And the number he got was huge, way, way larger than for, say, a hydrogen ion, which was the lightest known charged thing back then.
So that meant either a massive charge
or much more likely, an incredibly tiny mass compared to atoms.
Okay, so Thomson gives us, it's a particle, it's fundamental, it's negative, and we have this EAM ratio, but not E or M individually.
Exactly. You need one to find the other. And that's the problem Robert Millikan, working with Harvey Fletcher, tackled. The famous oil drop experiment starting around 1909.
Their goal was specifically to measure E, that fundamental unit of charge.
That was the objective, yeah. Measure the elementary charge directly.
So how does dropping oil help measure charge? Sounds a bit random.
Well, they sprayed this fine mist of oil droplets into a chamber between two horizontal metal plates.
Okay.
Now, some droplets would pick up static charge, maybe just from the spraying process, or they could zap them with X-rays to ionize them.
Okay, so you get charged droplets.
Right. And they watched individual droplets through a microscope as they fell under gravity. Then they applied a voltage across the plates,
creating an electric field.
Exactly. An upward electric force on the negatively charged drops. They could tweak the voltage.
Does some flow?
Or even move up.
Yes. They could suspend a droplet perfectly still, balancing gravity and the electric force. by measuring how fast it fell without the field, which let them figure out its mass using air resistance formulas, Stokes' law,
Right.
and then measuring the electric field needed to hold it steady, they could calculate the total charge on that specific droplet.
And the amazing part was, no matter which droplet they measured, the charge they calculated was always a whole number multiple, an integer multiple of one specific tiny value.
Never a fraction of it.
Never, always 1 times or 2 times or 3 times this base value.
So that smallest value had to be the fundamental unit of charge. That
had to be it. Direct proof that electric charge is quantized, it comes in discrete packets.
Wow.
And once they had a precise value for E, they could just plug that into Thomson's Eimer ratio.
And boom, you get the mass of the electron out.
And it was tiny, just as Thomson suspected. Incredibly small mass.
Okay, so now we have the electron as this tiny fundamental particle with a specific negative charge and a specific mass. Seems pretty solid. But then physics took a bit of a strange turn, didn't it?
A massive turn. Yeah, thanks to quantum theory. Louis de Broglie comes along in the 1920s with this, well, frankly, wild idea.
What was the idea?
He suggested, look, light acts like a wave, but Einstein showed it also acts like particles, photons. So maybe particles, like electrons, could also act like waves.
Whoa. Okay, that is a leap. How do you even test that?
Well, that's where the Davisson-Germer experiment comes in 1927. They basically provided the experimental proof.
What were they actually trying to do initially? Was it to prove de Broglie right?
Not directly, no. They were studying how electrons scatter, how they bounce off the surface of a nickel crystal.
Okay.
They fired an electron beam at this crystal and had a detector to see where the electrons went. Now, classically, you'd think...
They just bounce off kind of randomly, right? Like tiny balls hitting a bumpy surface. Maybe more bounce off at certain angles, but nothing too organized.
Exactly. You'd expect a smooth distribution, maybe. But what they saw was completely different.
What'd they see?
They saw sharp peaks and valleys in the number of scattered electrons at very specific angles. It looked exactly like the diffraction patterns you get when X-rays, which everyone knew were waves, scatter off a crystal.
Like light diffracting through grating.
Precisely. It followed Bragg's law for diffraction from a crystal lattice. This was not classical particle scattering. This was undeniable wave behavior.
So the electrons themselves were diffracting, acting like waves.
Yes, and the angles where these peaks occurred. They matched perfectly with the predictions if you assumed the electrons had a wavelength given by de Broglie's own equation. Lambda equals h over p, wavelength equals Planck's constant divided by momentum.
So it wasn't just like a wave. It had the wavelength de Broglie predicted.
Exactly. It was stunning confirmation, the first direct experimental proof that particles like electrons have a wave nature, a cornerstone for quantum mechanics.
And incredibly, around the exact same time, someone else confirmed it independently, J.J. Thomson's son.
George Paget Thomson, yeah. G.P. Thomson. In 1927, 1928, he used a different setup.
How is this different?
He used higher energy electrons and fired them through very thin metal foils. These foils were polycrystalline, made of lots of tiny randomly oriented crystals. Then the electrons hit a photographic plate behind the foil.
And what showed up on the plate? Not just dots.
Nope. Concentric rings. Beautiful, sharp rings.
Rings. Why is rings?
Because the electrons were diffracting off the randomly oriented crystal planes in the foil, it's the exact same kind of pattern you get from X-ray powder diffraction. It was completely analogous.
So another totally different experiment, same conclusion. Electrons diffract like waves.
Absolutely. Compelling evidence. And yeah, the irony is amazing. The father proves the electron is a particle. The son helps prove it's a wave. Both got Nobel Prizes for seemingly opposite findings.
That's fantastic. Okay, so particle, charge, mass, and wave nature. Check. What about the last piece? Spin.
Spin. It's a bit different. Its existence was actually proposed by theorists first, guys like Uhlenbeck and Goudsmit, to explain some tricky details in atomic spectra, how light from atoms splits in magnetic fields.
So theory came before the experiment this time.
Sort of. The key experimental evidence that pointed towards something like spin, something quantized related to angular momentum, actually came earlier. The Sturm-Gerlach experiment in 1922.
And what were Stern and Gerlach originally trying to test?
They were trying to test the idea of space quantization, whether the orbital angular momentum of an atom in a magnetic field was quantized, meaning it could only take on discrete values or orientations. Not electron spin specifically. That concept wasn't fully formed yet.
Okay, so how did their setup work?
They created a beam of neutral silver atoms. Silver was chosen because its magnetic properties are dominated by a single outer electron.
So the atom acts like a tiny magnet because of that electron.
Pretty much, yeah. They sent this beam of atoms through a very specific type of magnetic field. It wasn't uniform, it was inhomogeneous, meaning it had a gradient, it was stronger in one region than another.
Why the gradient? What does that do?
A non-uniform field exerts a force on a magnetic dipole, like our silver atom, and the direction and strength of that force depend on the dipole's orientation relative to the field gradient.
Okay, so what would you expect, classically, if the atom magnets could point any which way?
Classically, the magnetic moments could have any random orientation. So the magnetic field gradient would push them up or down or sideways by varying amounts. You'd expect the beam to just spread out vertically into a continuous smear on the detector screen.
Like fanning out.
Exactly, a smooth distribution. But that is absolutely not what they saw.
What did they see?
The beam split cleanly into two distinct spots. Just two. Nothing in between.
2 spots, that's it.
That's it. Totally unexpected. It meant the magnetic moment of the silver atom could only align itself in the magnetic field in 2 specific ways. Not a continuous range, just 2 discrete orientations.
And that's the evidence for electron spin.
Yes. Although it took a few years for the theory to catch up fully, this result was later understood as the first direct experimental proof of the quantization of electron spin. This intrinsic angular momentum that electrons just have, separate from orbiting anything.
And the 2 spots correspond to?
Spin up and spin down. 2 possible quantum states. The experiment showed that the magnitude of this intrinsic spin angular momentum is exactly 2, h bar over 2, where h bar is this fundamental unit of quantum angular momentum.
So it's like a tiny built-in magnet that can only point one of 2 ways.
That's a good analogy, yeah. It's a fundamental property, like charge or mass. Stern-Gerlach revealed it, even if they were initially looking for something else.
Amazing. Okay, let's wrap this historical journey up with maybe the most famous, most philosophically disturbing experiment of them all, the double-slit experiment, but done with electrons.
Ah, yes. The ultimate quantum weirdness test. While the concept comes from light experiments much earlier, doing it with individual electrons really drives the point home. Claus Jensen did it in the 60s, and then Tanimura and his team did incredibly precise versions in the late 80s.
And the basic idea is simple, right?
Yeah.
Fire electrons at a wall with 2 little slits in it.
Yep. 2 narrow parallel slits, and then you have a detector screen behind the wall to see where the electrons land.
So if electrons are just tiny particles, like miniature baseballs,
you'd expect them to go through either slit A or slit B. You just see 2 bands, 2 piles of electrons on the screen, lined up behind the slits. Simple addition.
that's not what happens when both slits are open.
Not even slightly. When both slits are open, what you see build up on the screen over time is a pattern of alternating bright and dark stripes. An interference pattern.
Interference, like waves.
Exactly like waves, like ripples on a pond overlapping, creating peaks where they add up and troughs where they cancel out.
Yeah.
This is classic wave behavior.
But these are individual electrons hitting the screen, right, one by one.
That's the most mind-boggling part. Even if you slow the beam down so only one electron goes through the apparatus at a time, over time, as you collect the landing spots of many individual electrons, that interference pattern still builds up.
Wait, so each electron interferes with itself? How?
That's the unavoidable conclusion. It seems each individual electron, when faced with the 2 slits, somehow behaves like a wave, spreads out, passes through both slits simultaneously.
And then interferes with itself before hitting the screen at a specific point.
Precisely. The wave nature dictates the probability of where the electron particle will be detected. High probability in the bright fringes, low probability in the dark fringes.
Okay, my head hurts a little. What happens if you close one slit?
Then the interference pattern vanishes instantly. You just get a single blob behind the open slit, exactly as you'd expect for particles going through one hole. The pattern only appears when both paths are possible.
And there's the observer effects, the which-way measurement.
Right. This is where it gets fundamentally weird. Suppose you try to be clever and put a little detector near the slits to see which slit each electron actually goes through.
Yeah, like a tiny little gatekeeper.
Exactly. Even the most gentle measurement imaginable, just enough to get that which-way information, the moment you do that,
the interference pattern disappears.
It disappears. Gone. The pattern on the screen reverts back to just 2 simple blobs, as if the electrons suddenly decided, oh, you're watching. Okay, I'll just act like a normal particle then.
So the act of knowing which path it took forces it to behave like a particle and destroys the wave interference.
Yes. The measurement itself fundamentally alters the outcome. You can know the path, particle nature, or you can see the interference, wave nature, but you can't have both at the same time for the same electron.
Wow. So this experiment just perfectly encapsulates that wave-particle duality, the self-interference, the role of measurement. It's all there.
It really is the quintessential demonstration of quantum mechanics in action. It highlights complementarity, the idea that these seemingly contradictory properties, wave and particle, are both aspects of the electron's nature, revealed depending on how you probe it.
What an incredible journey, seriously, from seeing glowing rays in a tube.
And figuring out they were negatively charged particles with this odd M ratio.
To Millikan nailing down that fundamental charge and letting us calculate the tiny mass am.
Then the shock of Davisson-Germer and G.P. Thomson showing these particles also act like waves, they diffract.
Uncovering that intrinsic quantum property, spin, thanks to Stern and Gerlach.
And finally the double slit, showing this wave stuff happens even one electron at a time, and that looking changes everything. These experiments literally defined our understanding of the electron.
And like you said, these aren't just history lessons. These properties are what make modern tech work.
Absolutely. Electron microscopes. They rely on the electron's short wavelength, its wave nature, to see incredibly small things.
Photoemission spectroscopy, understanding material.
Relies on analyzing electron energies and momenta. Spintronics, the future of memory and logic. That's all about manipulating electron spin.
It's amazing when you trace it all back. From a simple glowing tube to an electron interfering with itself.
It just hammers home how fundamentally strange the universe is at its smallest scales. Completely counterintuitive to our everyday experience.
It really does. And thinking about that double slit result again, the mere act of trying to know which path the electron took fundamentally changes its behavior, collapses that wave. What does that truly imply about reality?
Yeah.
You know, about the connection between observation and existence at that level, especially when, as you said, the technologies we build on these quantum rules, like the billions of transistors in the device you might be listening on right now, are so incredibly reliable and predictable when you look at the big picture. There's this profound disconnect between the bizarre quantum foundation and the classical world we experience. It really makes you wonder, just how deep does this rabbit hole go?